So this video gives a proof of the controllability matrix theorem. So the theorem runs like the following. So let's say we have the system with state equation as follows. Not surprisingly, x dot is equal to ax plus bu, where here A is an n by n matrix of reals. So this system with the state equation is controllable if the rank of a matrix E, which we're about to create, is equal to n. And we're defining E as the following way. So we're going to compose it first with a column or columns of B, and then a column or columns of AB, A squared B, all the way to A to the n minus 1 times B. And E is called the controllability matrix. So in this video we're going to show the proof that constructs E and that E's rank gives you controllability of the system. So the method of proof is the following. So the first thing that we're going to do is that we're going to show that the similarity transform So a similarity transform gives us a different state for the system. So we're going to use a similarity transform PA, P inverse, which we're going to call A bar, and PB is equal to B bar. And here P and P inverse are computed from E and E inverse. So we're going to show that this similarity transform results in some system A and B, which is in controllable canonical form. So that's step one. We're going to show that that similarity transform, based on the E that we defined before, gives us controllable canonical form. Then we're going to show that any system that is in controllable canonical form is controllable. So here we're going to use a single input, single output case for simplicity, but the proof can be shown in general. All right, so with this the case, let's start with step one of our proof. So remember, in step one, we're starting by using this matrix E that we defined. So our first step is that we need to assume that E is invertible. And because we're talking about the single input, single output case, E is going to be a square matrix. So we're going to assume that E is invertible and that the system A bar, B bar that we create using the similarity transform is in controllable canonical form. So now we're going to take, again, PA P inverse is equal to A bar. So this means, if we do a little bit of math on either side, that we can write this as P times A times P inverse times P is equal to A bar times P. And so this is actually equal to P times A. This is actually easy to show here because P inverse times P is just the identity matrix. So P times A is equal to A bar times P. Okay? And again, P times B is equal to B bar. So let's let the rows of P be defined as P1, P2, P3, etc. So we know that A bar times P is equal to P times A. We showed that here. So let's go ahead and write now A bar times P. So A bar, which is in controllable canonical form, as we said before in our assumption. So now A bar is equal to 0, 1, 0, and then a whole bunch of other zeros. 0, 0, 1, and a whole bunch of other zeros, until we get to a row where we have all zeros that ends in a 1. And then because we're in controllable canonical form with A bar, we know that we can write minus A0 minus A1 minus A2 all the way to minus A n minus 1. So this is our A bar matrix. And A bar times P, we defined that P was equal to a row P1, a row P2, all the way to a row Pn. So A times P is equal to P times A. So P times A is just the product of P1 times A, P2 times A, all the way down to Pn times A. Okay, so we have A bar, and then we have P, and then this is the product of P times A here, which we've chosen to write this way. So now, if we were to write the products row by row, we would be able to show that P2 is equal to P1 times A. Interesting. Why is this the case? Well, it's the case because P2 represents this row. So in this row we have P1 times A. So P1 times A we're choosing to represent by the rows of P. So as we go to multiply this first column, or this first row here, times all the columns and all the rows that we see in the matrix here for P. So now we see that we multiply 0 times P1 plus 1 times P2, etc., 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 and that's going to be equal to P1 times A. So because of the way that our matrix is structured, P2 is equal to P1 times A. P3 will be equal to, because we take now 0 for P1, 0 for P2, 1 for P3, will be equal to P2 times A. So P3 is equal to P2 times A, but P2 was equal to P1 times A times A. So this is equal to P1 A squared. And we can show now for any P4, this is equal to P3 times A, which is equal to P1 times a cubed, etc., 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 until we get to Pn is equal to Pn minus 1 times a, which is equal to P1 times a to the n minus 1. Interesting. So now we have a way to describe each row of P, P1, P2, P3, as the product of P1 times a bunch of A's. Likewise, if we start with B bar is equal to P times B, B bar, as we know from controllable canonical form, is a bunch of zeros until we get to a 1. And this is equal to P1 times P1 times B, P2 times B, until we get to Pn times B. So here we have P1B equals 0, P2B is equal to 0, but we know that P1 is equal to, we know that P2 is equal to P1 times A, and we know that from the previous page. So now we can write that P1 times A times B is equal to 0. P3 times B is equal to P1A squared times B, and that's equal to 0, all the way to Pn times B is equal to P1 times A to the n minus 1 times B, and that is equal to 1. So we have a whole bunch of zeros here, and again, because P2 is equal to P1 times A, P3 is equal to P1 A squared, P4 is equal to P1 A cubed, etc. We know that from the previous page. So with this system of equations for B and A equal to 0, we can start to factor out P1 from the various pieces of the system. So now we're going to write it as P1 times B, P1 times AB, P1 times A squared B, all the way to P1 A to the n minus 1 times B. This is equal to 0, 0, 0, all the way until we finally have a 1 at the end. And so what I can say now is I can factor out P1. So P1 is going to be equal to, we'll say it like this. So P1 times B times AB times A squared B, all the way to A to the n minus 1 B, is equal to 0, 0, until we finally get to a 1. So this matrix here is the matrix E that we defined before. B, AB, A squared B, etc., etc., etc. So I can say now that P1 is equal to a bunch of zeros times the inverse of E. Why does this make sense? Of course, this ends with a 1 here. So P1, if I define this as E, then I can say P1 times E is equal to 0, 0, finally in a 1, times nothing. So P1 is equal to, I'll just make sure that this is clear here. So I'm going to post multiply both sides by E inverse. And so now we see that this will become an identity matrix here. So P1 is equal to 0, 0, until we finally get to a 1, times E inverse, where E here is not the eigenvector or the eigenvalue, it's the matrix that we defined as the controllability matrix. So this gives us some value for P1. So if we have P1, now we can construct all the rows of P. So the first thing that we're going to do is we're going to compute, we'll call this part A. So we're going to compute E is equal to is equal to B, and then AB, and then A squared B, all the way to A to the n minus 1 times B. And then we're going to compute we're going to compute P. And P is going to be computed as P1, P2, all the way to Pn transpose. So we're using rows of P1, P2, P3, etc. So P1 is equal to 0, 0, 0, and then finally a 1 times E inverse. P2 is equal to P1 times A. P3 is equal to P2 times A, which is equal to P1 times A, which is equal to P1 A squared, until we get to P sub n is equal to P1 times A to the n minus 1. So now we can say that A bar and B bar is equal to PA inverse and P times B, and it is in controllable canonical form based on how P was constructed. So now we've shown part 1. So it's interesting to ask yourself, how do we know that P inverse exists? And the answer actually makes sense as long as you think about the fact that we're producing for the answer to P, right? So P we're defining as a bunch of rows, P1, P2, all the way to Pn. And these rows are made up of our definitions of P1, P2, etc. So P1 times B times AB, A squared B, etc., all the way to An minus 1 times B. This is going to be equal to 0, 0, until we finally have a 1 at the end. So P2 is equal to P1 times A. And so what we're going to have is P2 is equal to P2 is multiplied by B times AB times A squared B, all the way to A to the n minus 1 times B. And so this is going to be equal to 0, 0, until we get a value for 1 here, and some possibly non-zero value after the 1. So we've already found P1. It's a bunch of zeros that ends in a 1. P2 takes the same matrix that we just multiplied by P1, squares it, and then allows us to have this value which is possibly non-zero at the end. So as we add now P3 times the same matrix, this is going to give us a 0 and a 0, finally a 1, and then 2 potentially non-zero values after. So we're building a matrix after as we get to the end of everything. P times our controllability matrix E is going to be 0, 0, until we finally have a 1 on the diagonal here. And then we're going to have a bunch of potentially non-zero values here. So our matrix is lower triangular. And we're going to be able to say that P will always exist because we're always going to be able to make E inverse. So because we can create E inverse, we know that P will always exist. And we actually will know that P inverse will always exist since E will always exist and this matrix here will always exist. So for these assumptions, we know that we'll always get some invertible matrix P. So that's just a little aside to make you realize that P inverse will be a real matrix and we can actually create it. So now let's continue on with the proof of part 2. So in this proof, once we have a controllable canonical form, we can use state feedback to place our closed loop poles anywhere we'd like. So let's remind ourselves that we produced some matrix A bar here, which is in controllable canonical form. And then we have minus A0, minus A1, all the way to minus AN minus 1 here. So that's our matrix A bar, and B bar is equal to 0 until we finally get to a 1. So let's now say that we pick some feedback controller F as F1, F2, and it has to have the full rank, so we have to go to Fn. So with this choice, then we can write our system of equations. So we can say A minus some value B times F is equal to 0, 1, 0, 0, 1, etc. And we're finally going to have values that show up only on the very last level. So here we'll still have a 1, all zeros here. And now finally we'll have minus A0 minus F1, minus A1 minus F2, etc. until we get to minus AN minus 1 times minus F sub n. So this gives us our feedback matrix A once we've calculated A minus BF. So in order to find out where our poles are going to be, we need to calculate the determinant of lambda I minus A minus BF. So this determinant will give us the eigenvalues of A minus BF. So now we can write those eigenvalues in that determinant because we have this really nice matrix that's mostly zeros. So our value for the determinant will be lambda to the n plus A sub n minus 1 plus F sub n lambda to the n minus 1 plus A sub n minus 2 plus F sub n minus 1 times lambda to the n minus 2, etc., etc., plus A0 plus F1 as our final value will be equal to 0. And so our desired closed-loop polynomial, if we choose to call this value here, for example, alpha 1, and we'll call this alpha 2, all the way until we get to alpha n minus 1. Sorry, alpha n, because that goes all the way to F0, or to A0. So now we can rewrite our equation as lambda to the n plus alpha 1 lambda to the n minus 1 plus alpha 2 lambda to the n minus 2 plus until we finally get to alpha sub n is equal to 0. And so now we can solve the equation as f1 will be equal to alpha sub n minus a0. So a0 is going to be obtained from here, right? So our value f1 comes uniquely from a0. f2 will be alpha sub n minus 1 minus a1. f3 will be alpha sub n minus 2 minus a2, all the way until we get to f sub n will be equal to alpha sub 1 minus a sub n minus 1. So because these equations give us the desired feedback law, and because we know that this is a unique polynomial, and we know it's a unique polynomial based on the structure of our original matrix. So this shows us that we can construct the feedback law from the controllable canonical form. So this is the end of part 2 of the proof.